So in today's video, we'll be discussing about Physics Paper 2 AS Level Structured Question 2024 May-June, variant is 23 and the subject code is 9702. Question number 1. The drag force Fd acting on a sphere falling through a liquid is given by Fd is equal to this equation where r is the radius of the sphere, v is the speed, and this sign is the viscosity. So this is viscosity. Show that the SI base unit of viscosity are kilogram per meter per second. So first of all, we need to make the viscosity becomes the subject of formula. So viscosity is equal to Fd by the whole equation. That is 6 pi Rv. So we know that force is equal to mass into acceleration, and for mass the SI unit of mass is kg, and for acceleration it is meter per second square. So kg meter per second square, and 6 pi has no unit, r has a SI unit of meter, and v has a SI unit of meter per second. So m and m cancels, and the final unit becomes kg per meter, and second to the power -2 and second to the power -1. So second to the power -2, and since it is divided, so minus -1, that is second to the power -1. So it is -1. So this is same as shown. At B, the sphere has a radius of 3 cm and is falling vertically downward at a terminal velocity of 2 meter per second. So the sphere is falling with a terminal velocity of 2 meter per second through the liquid. The drag force acting on the sphere is given. So calculate the viscosity of the liquid. So again, we make the viscosity becomes a subject of formula. Then we know the value of drag force 6 pi, and we know the radius, that is in centimeter. So we must convert this to meter. And what is v? So it is terminal velocity. For terminal velocity, we know that resultant force, that is F net, is equal to 0. That means the upward force is equal to the downward force. So the resultant force is 0. That means terminal velocity is the constant velocity of 2 meter per second. So after substituting the value, we get our answer in this form, that is approximately 0.085 to the answer given. You have to remember that we have given the answer to two significant figure. That is, if we write this answer in this form, then you would understand clearly, that is 1, 2. So 8.5 into 10 to the power -2. So 1, 2. So this answer is two significant figures. Part C. On figure 1.1, draw a label arrow to represent the direction of the three forces acting on the sphere as it falls at a terminal velocity through the liquid. So since the sphere is falling at a terminal velocity, that means terminal velocity is a constant velocity where the resultant force, that is F net, is 0. Since the resultant force is 0, so the upward force must equal to the downward force. And we know that the downward force for the sphere, that is the weight that is acting vertically downwards from its center. Since the sphere is a uniform object, so its mass is concentrated at the center, so the weight is acting from the center, that is vertically downwards. And we know that the drag force is given, that is the drag force. So the drag force is the resistive force due to the liquid. So resistive force due to the liquid, so it is acting upward. And we know that upthrust is also acting, since the sphere is falling through the liquid or inside the liquid, so upthrust is acting. And we know that upthrust is equal to rho Vg, where rho is the density of the liquid, v is the volume of the object, and g is the gravitational field strength, that is 9.81 for physics and 10 for mechanics. So by using this formula, we can calculate the upthrust, and the upthrust is acting upward. So then for part D1, the density of the liquid is given. Show that the upthrust acting on the sphere is 1 Newton. So we need to find the value of upthrust. So we know the formula, that is upthrust is equal to rho Vg, where rho is the density of the liquid, v is the volume of the object, and g is the gravitational field strength, that is 9.81. So density, that is 920, and the volume, so for the volume of the sphere, so for a sphere, we know the volume, that is equal to 4 by 3 pi r cube. So 4 by 3 pi r cube, 4 by 3 pi r cube. And what is the radius? So initially we have given the value of radius that is 3 centimeter. So we must convert this 3 centimeter to meter. That is 3 by 100. That is radius. And since radius cube, so power cube into 9.81. So the upthrust comes to be this value. That is approximately 1, 2, 3. So it's a significant figure, but we need to give our answer to two significant figures, that is 1, 2. So it is 1.0 Newton to 2 SF as shown. And for part 2, calculate the mass of the sphere. So to calculate the mass of the sphere for this question, so we know that downward weight, since the object is moving at a terminal velocity, that means at a constant velocity, so the upward force must equal to the downward force, that is weight is equal to the downward weight force is equal to the upward Fd plus upthrust. So weight is equal to Fd plus upthrust, that is W is equal to Fd plus upthrust, where we know that the drag force, so the drag force value, that is 0.096. So we know the value of drag force, that is 0.096, and the upthrust we have found, that is 1.0 Newton. So 1.0 Newton. So what is the weight? So we have calculated the value of weight from these two values. So we know that weight is equal to mass into gravitational field strength. So mass is equal to weight by gravitational field strength, that is 9.81. So we get the mass as given. So we write our answer as two significant figure, that is 0.11. So 0.11 to 2 SF. For question 2 part A, define displacement from a point. So the displacement from a point, so suppose this is one point, starting point, and this is the ending point. So starting and ending. So this is the distance traveled. So this is the distance traveled. And for displacement, displacement is from the starting point to the ending point, and it is a straight line. So it is a straight line. That is a straight line from the starting point to the ending point. So the displacement is the distance from the starting point, or from the point, distance from the point in a straight line. So distance from the point, so distance from the point in a straight line. So in a straight line in a given direction. So in a straight line in a given direction. So displacement is the distance from a point in a straight line in the given direction. Number 2, part B. An object is projected horizontally at a speed of 6 meters per second. So the object has a horizontal speed of 6 meters per second from the slope as shown in figure 2.1. The slope is at an angle of theta to the horizontal. Here resistance is negligible. So here air resistance is negligible. That means there is no air resistance. The object lands on the slope a time of 0.71 second later and stop without rolling or bouncing. So the object lands on the slope. So the object here moves from this point and then moves like this and then again lands on the slope. So the object lands on the slope after a time of 0.71 seconds without rolling or bouncing. Determine the horizontal distance traveled by the object. So what is the horizontal distance traveled by the object? So we know the formula S is equal to ut plus half at square, and we know the for the horizontal direction, for the horizontal distance we know the horizontal speed, that is the horizontal speed. So we know the value of horizontal speed and the value of time. So horizontal speed and time. And what is acceleration? So acceleration is 0 because here we put acceleration 0 because let's suppose for the object at this point, so there is no forward force given in the question. So there is no forward force and the object has already been released. So for this object, the object has already been released and there is no forward force acting on the object. So there is no forward force acting on the object, and since air resistance is negligible, so as the object moves from this point to this point like this, so that as the object moves, there is no air resistance given. Since there is no air resistance given, that means there is no backward force. So there is no forward force, and since there is no air resistance, so there is no backward resistive force due to air resistance. So here we can see that the resultant force is 0. Since the resultant force is 0 and we know that force is equal to mass into acceleration, so the acceleration is also 0. So after substituting the value, we get a distance of 4.26 meter, that is approximately 4.3 meter, to two significant figures, that is one significant and two significant figures. Then determine the vertical distance traveled by the object. So for the vertical distance, so for this object, we need to find the vertical distance from this point to, let's suppose, this point. So what is the vertical distance? So S is equal to ut plus half at square. And for the vertical distance, here initially we know the horizontal velocity. So we know the value of horizontal velocity, and since there is no vertical velocity given, so the velocity in the vertical component or in the vertical direction is 0. So initially there is no vertical component of velocity. Therefore the vertical component of velocity is 0, and the total time is 0.71 plus half. Acceleration is 9.81 into t square. Why the acceleration is 9.81? Let's suppose for the object at this point, so the weight is acting vertically downward, and since the weight is acting vertically downward, so weight is equal to mass into acceleration, mass into gravitational field strength, and since weight is acting vertically downward, so the gravitational field strength is also acting vertically downward, and we know that gravitational field strength is equal to 9.81. So the acceleration is 9.81, and there is no air resistance, so the acceleration remains the same, that is 9.81. So by using this formula, we calculate the vertical distance traveled by the object, that is 2.4726, that is approximately 2.5 meter, to two significant figures. Use your answers from B1 and B2 to calculate theta. So what is the value of theta? So theta is this given angle. So we need to find this value of theta. Let's suppose for the object moves from this point to this point, and what is the value of theta? So since this side is horizontal to this side, so if this angle is theta, then this angle is also theta. And what is the horizontal distance and the vertical distance traveled by the object? So the horizontal distance traveled by the object is 4.3 meter. So the horizontal distance is 4.3 meter. And for the vertical distance, what is the vertical distance traveled by the object? That is 2.5 meter. So the vertical distance is 2.5 meter. So what is the value of theta? Tan theta is equal to opposite by adjacent. So by using this formula, we can calculate the value of theta. That is this is the horizontal distance and this is the vertical distance. So tan theta is equal to opposite by adjacent. So theta is equal to 38.17, that is approximately 30 degree. Then determine the magnitude of displacement of the object from its original position. So displacement, that means from the initial position to the final position, what is the total displacement? That is, displacement is always a straight line, and it is from the starting point to the ending point. So from the starting point to the ending point, a straight line. That means we know the horizontal distance and the vertical distance. So if we find the hypotenuse, then we can calculate the displacement. That is from the starting point to the ending point and a straight line in one direction. So displacement square, that is displacement square, we consider as d square is equal to 4.3 square plus 2.5 square. So displacement comes to be 4.973 meter, that is approximately 5 meter. So we have given our answer to two significant figures, that is 1, 2. By considering the energy, calculate the speed of the object just before it lands. So speed of the object just before it lands. By considering energy, calculate the speed of the object just before it lands. So speed of the object just before it lands, that means from the starting point to the ending point, when the object lands, we need to find the speed of the object. So to find the value of speed, so you have to remember that by using this energy method, that initially and finally. So initially we have kinetic energy, gravitational potential energy, and work done by driving force. And finally we have kinetic energy, gravitational potential energy, and work done against resistance. So you have to consider the three energies for initially and three energies for finally. So for kinetic energy is equal to half mv square, and we have not given the value of mass in this question, so we consider the mass as m, and initially we have a speed of 6 meter per second, it is horizontally. So half mv square where v is the speed. So half mv square. So 18 m, where m is the mass. Then gravitational potential energy is equal to mass into gravitational field strength into height. So what is the vertical height? Vertical height is, so for gravitational potential energy, we need to consider the vertical height, that is from the starting point to the ending point. What is the vertical height? So this vertical height. So this vertical height is the vertical displacement, and we know that vertical displacement is 2.5 meter. That is the vertical displacement. So by using this, we calculate the value of gravitational potential energy and what done by driving force. So initially in the question, we have not given the value of what done by driving force. That is, there is no driving force given. Since there is no driving force given, so we can consider that the what done by driving force is zero, since there is no driving force given. Then for finally kinetic energy, so half mv square, where we consider the final speed as v square as v. Then for finally, suppose the object lands from the starting point to the ending point, and as the object lands from the starting point to the ending point, so we consider the point where the object lands is the horizontal ground. So we consider this point as the horizontal ground. Since the object is now at the horizontal ground, so here the vertical height is 0. So the vertical height is 0, and the vertical height from this horizontal ground to the starting point is the vertical displacement, that is 2.5 meter. And finally, we consider the object lands to the vertical ground. We consider that the object lands on the vertical ground, horizontal ground. That is, after the object traverses this vertical displacement, the object lands to this point, and we consider this point as the horizontal ground. So, as the object lands on the horizontal ground, so the vertical height is 0. That is, the gravitational potential energy is also 0. So gravitational potential energy is 0 because gravitational potential energy is equal to mass into gravitational field strength into height. And since we consider the object where it lands is the 0 height, so the height is 0. And what done against the distance? So there is no what done against the distance given. There is air resistance is negligible, and there is no what done against the distance given. So it is 0. So by equating initial is equal to final, we consider the value of v as 9.2 meter per second. That is approximately 9.2 meter per second, or negative 9.2. So negative is inadmissible or not acceptable, and our correct answer is 9.2 to 2sf as the final speed. For question number 3, state Hooke's law. So for Hooke's law, we know that force is directly proportional to extension. So for Hooke's law, we know that force is directly proportional to extension. So applied force is directly proportional to extension, so it is directly proportional, or you can write proportional as you wish, but the more appropriate is directly proportional. That is, force is directly proportional to extension. The variation of the applied force with the extension for the sample of a material is shown in figure 3.1. So force against extension and the object obeys Hooke's law. That means a straight line, that is, force is directly proportional to extension, and initially when force is 0, the extension is also 0. The sample behaves elastically up to the extension of 80 mm and breaks at point X. So the sample behaves elastically. So what is elastically? So for elastic deformation, we know that when the force is removed, so when the force is removed, the object returns to its original shape or size. So for elastic deformation, when the force is removed, that means when the force becomes 0, the extension becomes 0, and when the force becomes 0 and the extension becomes 0, we can say that the deformation is elastic deformation. That is, in elastic deformation, the object returns to its original shape or size when the force is removed. The object returns to its original shape or size when the force is removed. And for elastic limit, so this is the limit of proportionality, that is, force is directly proportional to extension, or this is a straight line. So this line is a straight line, that is the limit of proportionality. And after this point, this is the elastic limit. So elastic limit is the maximum force that can be applied to the object such that the object returns to its original shape or size when the force is removed. That means it is the maximum force that can be applied to the object such that the object returns to an extension of 0. So this is the maximum force that can be applied to the object such that the object returns to an extension of 0. So here we can see that the object returns from this point to an extension of 0. So here this point is the elastic limit. That means this is the maximum force. After elastic limit, the object have a extension that is like this. So this is the extension, but for elastic limit, this is the maximum force that can be applied to the object such that the object returns to its original shape. That means extension of 0. So elastic limit is the maximum force that can be applied to the object such that the object returns to an extension of 0. Then for plastic deformation, so from the starting point to elastic limit, this is elastic deformation. Why this is elastic deformation? Because the object returns to an extension of 0. Then for after elastic limit, this is plastic deformation. That means when the force is removed, the object have some extension. Since the object have some extension, so this deformation is called plastic deformation, while up to elastic limit, the deformation is elastic deformation. Then on the line in figure 3.1, draw a cross to show the limit of proportionality. Label this cross with letter P. So we know that limit of proportionality is the point at which force extension graph becomes non-linear or not a straight line. And up to limit of proportionality, this is a straight line. Straight. That is force is directly proportional to extension. So force is directly proportional to extension or a straight line up to this point. So we can consider this point as the limit of proportionality. And this point has a value of 60 and 5.4. So 65.4, this is the limit of proportionality. This is our limit of proportionality at 65.4. Then on the line in figure 3.1, draw a cross to show the elastic limit. Label the cross with letter E. So we need to draw a cross at the elastic limit. And what is elastic limit? Elastic limit is the maximum force that can be applied to the object such that the object returns to an extension of 0. So elastic limit is at this point. So the sample behaves elastically up to 80 mm. That means up to 80 mm, the extension is elastically. So up to 80 mm, that is up to 80 mm, the extension is elastically or the deformation is elastically. Since up to 80 mm, the deformation is elastically, so we can consider this point as the elastic limit. That means after this point, the wire starts to become or deform plastically. That means this is our elastic limit. So this is our elastic limit, and so the elastic limit is at 80 and 5.9. So 80 and 5.9, that is the elastic limit, which is the maximum force that can be applied to the object such that the objects deform elastically or the object returns to its original position at an extension of 0. So this is our limit of proportionality, this is our elastic limit. Then for part C, the sample MB has a cross-sectional area of 0.40 mm square and an initial length of 3.2 meters. For deformations within limit of proportionality of the sample, determine the spring constant of the sample. So for the deformation up to limit of proportionality, we need to find the spring constant K. So spring constant up to limit of proportionality. So we know that spring constant is equal to force by extension. That is force is directly proportional to extension. That is force is equal to spring constant into extension. So spring constant is equal to force by extension. So force by extension up to limit of proportionality. So this is the limit of proportionality, and this point has a value of 60 mm and 5.4 Newton. So 5.4 Newton and 60 mm. So 60 mm. So we need to convert this to meter. So 60 into 10 to the power minus 3 meter. So the spring constant comes to be 90 Newton per meter. So 90 Newton per meter. Then the Young modulus of the material from which the sample is made. So we need to find the value of Young modulus E. So Young modulus is equal to stress by strain, and we know that stress is equal to force per unit area divided by strain. So divided by strain, strain is equal to extension divided by original length. So force per unit area. So if we just convert the divide sign to multiply sign, then we have to reverse this values. That is, length comes above and x below. So FL by AX. So by using this formula, we can calculate the Young modulus up to limit of proportionality, because we have to calculate the values for up to limit of proportionality. So Young modulus is equal to force, and we know that the force value at this point is 5.4 Newton. So force into original length. So the original length is given as 3.2 meter divided by area. So what is the cross-sectional area? So we must convert millimeter square to meter square. So we know that 1 meter is equal to 100 centimeter, and 1 meter is equal to 100 centimeter into 10, that is 1000 millimeter. So 1 meter square is equal to this much millimeter square. So 1 millimeter square is equal to 1 by 10 to the power 6 meter square, that is 1 into 10 to the power minus 6 meter square. So 0.40 millimeter square is equal to, we need to multiply this value with 0.40 to calculate the area in terms of meter square. So area in terms of meter square. And what is the extension? So extension is from the starting point up to the limit of proportionality, and the extension is 60 millimeter. That is 60 millimeter. So 60, and we must convert millimeter to meter, that is 10 to the power minus 3 meter. So after substituting the value, we get the Young modulus as 7.2 into 10 to the power 8, two significant figures. Then determine an estimate of the work done on the sample as it is extended from zero extension to its breaking point. Explain your reasoning. For part D, determine an estimate of the work done on the sample as it is extended from zero extension to its breaking point. So work done from zero extension to its breaking point. So we need to calculate the value of work done. So what would be the work done? So for the forced extension graph, so first of all, for velocity time graph, we know that the area under the velocity time graph is the displacement. So velocity is equal to displacement by time. So displacement is equal to velocity into time. That means area under the velocity time graph is the displacement. Similarly, we know that work done is equal to force into distance. So force and the distance is the extension. So work done is equal to force into distance. That is force and distance. That is extension. Similarly, velocity and time. So velocity and time. So here we can see that the area under the velocity time graph is displacement. So the area under the force extension graph must be work done. So we can relate this. So the area under the force extension graph is the work done. That is, the area under the force extension graph is our work. So we need to calculate this value of work. And you have to remember that we need to just estimate. So we need to just estimate. So if we consider the total diagram, then the total diagram is like a trapezium. So we can calculate this area by using the area of the trapezium. That is, area of the trapezium is equal to half into sum of two parallel sides into height. So this is the formula. Then work done is equal to half into sum of two parallel sides into height. So we need to find the two parallel sides. That is, the two parallel sides are this side. That is one parallel side. So this is our trapezium. So area of the trapezium is half into sum of two parallel sides, that is this parallel side and this parallel side, and vertical height, that is height. So half into sum of two parallel sides, and the parallel side is approximately 192 millimeter, and this side is approximately from this point to this point is 112 millimeter. So we have to just get an approximate value. So 192 and 112 millimeter. So we might convert this to meter, that is 10 to the power minus 3 meter. Then what is the vertical height? So the vertical height, so we consider the vertical height from this point to this point, that is approximately 6 Newton. So the approximately it is 6 Newton. So the vertical height is approximately 6 Newton. There is 6 Newton. So the work done we get is 0.912 joules. That is approximately 0.91 joules. That is two significant figures. So we calculate the area for this trapezium. But you have to remember that there is also a small triangle here. So we need to calculate this area also. So we have calculated the area of trapezium. Now what is the area of this small triangle? So area of this triangle, that is half into base into height, half into base into height. So what is the value of base? So this is approximately 120, 160. So we need to take approximately this length is 140 millimeter. So 140 millimeter, and this length is 192. So 192 minus 140, and we need to convert millimeter to meter, that is 10 to the power minus 3 meter. So this is the base, and what is the vertical height? So from 6 to up to this point, that is 6.1234. So 6.4. So 6.4, 6.8, because this length is 7. Since this length is 7, so this value is obviously 6.8 into 6.8. So what is the area of this small triangle? So 192 minus 140 into 10 to the power minus 3 divided by half into 6.8. So this is 6.8, and we need to consider this vertical height. So from 6 to this point, so 6.8 minus 6, that is 6.8 minus 6, that is 0.8. So 0.8. So the answer we get is 0.0208, that is 0.0208. So what then is the area of the trapezium plus the small triangle that we need to consider. So the trapezium plus the area of the triangle, that is 0.0208. So what is the total work done? So 0.912 plus this value, that is approximately 0.9328, that is approximately 0.93. So the work done we get is 0.93, not 0.91. So this is our final answer. A second sample of the same material has a larger cross-sectional area. So the same material means they have the same Young modulus and has a larger cross-sectional area. So the cross-sectional area of the second wire is, or the second sample is more than the original sample, but the same initial length. So the initial length, that is L, is same. The two samples are each deformed with the limit of proportionality. So both are deformed up to limit of proportionality. Study and explain qualitatively how the spring constant of the second sample compares with that of the original sample. So how the spring constant varies. And for spring constant, we know that spring constant is equal to force per unit extension. So force per unit extension, and we need to find that how the spring constant of the second sample varies compared to the first sample. So Young modulus is same. So we can use the formula, that is Young modulus is equal to force per unit area extension divided by original length, and Young modulus is same because they are the same material. So Young modulus is same, and also the same initial length. So the initial length is same. And so for this question, here the only thing that varies is the cross-sectional area. So cross-sectional area is varying, and we need to find the varying in spring constant. So we can replace spring constant by force per unit extension. So instead of force per unit extension, we can replace this with spring constant. There is force per unit extension. So we replace force per unit extension with spring constant by into length by cross-sectional area, and the area has increased. So then we make spring constant become the subjective formula. That is spring constant is equal to area into Young modulus by length, and length is same. Young modulus is also same, and as area increases, we can see that the spring constant also increases. Since as both are the Young modulus and the length are same, so spring constant is directly proportional to area. So as the area increases, the spring constant increases. So the spring constant is proportional to area. So spring constant is proportional to area. So the spring constant of the second sample will be greater. Since area increases, so spring constant also increases. For question number 4, a progressive transverse wave traveling from left to right is shown at an instant in time in figure 4.1. So from left to right, and it is shown in figure 4.1. This is the duration of travel. R and T are the points on the wave. So R and T are the point. State the phase difference between point R and T. So we need to remember that this is a progressive wave and not a stationary wave. If it is a stationary wave, then since the 2 points are separated by a node, so the phase difference would be 180 degree for stationary wave, or if they are in the same phase, that means if they are within the same node, that is this two node, and the point T is like this or like this, then they have a phase difference of 0 degree. This is for stationary wave. But for progressive wave, what is the phase difference? So phase difference, so for a complete wave, that is from this point to this point, the total phase difference is 360 degree. 360 degree. So for one wave, the phase difference is 360 degree. That means from this point to this point, this is the one wave, so 360 degree. So we can divide the 360 degree into 4 parts, that is from this part to this part, that is 90 degree. Then from this part to this part, this is 90. This is also 90. And from this part to this part, this is 90. So 90, 90, 90, 90. In total 360. So from R to T, the variation is 90 degree, 90 degree and 90 degree. That is 390 degree. So if we add this, we get a phase difference of 270 degree. So the phase difference is 270 degree for the progressive wave, progressive transverse wave. In figure 4.1, on figure 4.1, draw an arrow at point T to show the direction of movement of point T at the instant shown. Now, what is the movement of point T? So what is the movement of point T? So for this movement, we need to look at the wave before it. So before point T, we can see that the wave is downward. So the point T also moves downward. And let's suppose any random point, suppose this point. What is the movement of this point? Since the wave before this point is moving upward, so we can see that this is moving upward. So this point also moves upward. Similarly, for T, before T, the wave is moving downward. Since the wave is moving downward, so T is also moving downward. So the direction is vertically downwards. Then the horizontal distance between R and T is 0.62 centimeter. So R and T is 0.62 centimeter as shown in figure 4.2. The speed of the wave is 0.27 meter per second. Calculate the frequency of the wave. So we need to find the frequency. So first of all, what is the wavelength? So wavelength is for one complete wave. So one complete wave is completed at this point, from this point to this point. So the total wave, that is one complete wave, is from this point to this point. And 0.62 is 1, 2, 3. So 3/4 of the wave. 0.62 is 3/4 of the wave, or we can consider that 3 box. So 0.62 is 3 box. It is 1 box, 2 box, 3 box, and 4 box. 4 box is 1 wave. That is, this is 1 box, 2 box, 3 box. So 3 box is 0.62. So what is the 4 box or 1 complete wave? So 1 complete wave is 0.62 by 3 into 4. So we get the value of wavelength. This is 1 wavelength. Now we know the value of wavelength and we know the speed. So V is equal to F lambda. So F is equal to V by lambda. So V by lambda, that is, we know the value of speed and we have found the wavelength. So we get a value of frequency, that is 32.66 Hertz, and we write this to 33 Hertz, that is two significant figures. For part D, the wave is a water wave produced by dipper S1 attached to a vibrator in a repel tank. An identical dipper S2 is attached to the same vibrator. The two dippers produce an interference pattern on the wave on the water in the tank as shown in figure 4.3. So the two dippers and the produce wave crest. So these are the wave crest and these are the wave trough. So crest, trough, crest, trough. Now, the wave crests from each source are represented by solid lines on figure 4.3. So the crests are the solid lines and the wave trough are represented by the dashed line. So crest is the solid line and the trough is the dashed line. A point P in figure 4.3. So a point P in figure 4.3. At point P in figure 4.3, the wave from S1 has the same amplitude as the wave from S2. So both the waves have the same amplitude. Describe and explain the amplitude of the resultant wave produced at P. So what is the amplitude of the resultant wave produced at P? And the wave produced by S1 and S2 have the same amplitude. So at point P, we can see that the crest and trough meets. So suppose a crest meets with a trough. So if we just draw this like this, then this is the baseline and crest meets with a trough. So we can see that as they both have the same amplitude, so the resultant amplitude becomes 0, or the resultant wave has 0 amplitude. So crest meets with the trough and the resultant amplitude is 0. So the resultant displacement is the sum of the displacement of the wave from S1 and S2. Resultant displacement is obviously the displacement of the S1 and S2. So resultant displacement is the displacement of S1 and S2, and at point P, both the waves from S1 and S2 interfere destructively. So destructive interference occurs because crest meets with the trough, and constructive interference occurs if crest meets with a crest. But for now, destructive interference occurs. Therefore, the resultant amplitude of the wave is 0. So the resultant amplitude is 0. Number 5, part A. State Kirchhoff's second law. So first of all, for Kirchhoff's first law, it is about conservation of charge, and for the second law, it is the conservation of energy. First law is the conservation of charge and second law is the conservation of energy. And for Kirchhoff's first law, we know that the current entering a junction is equal to the sum of the current leaving the same junction. There is I is equal to I1 plus I2 plus I3. So this is for the Kirchhoff's first law. That is, the sum of the current entering a junction is equal to the sum of the current leaving the same junction. Sum of the current entering a junction is equal to the sum of the current leaving the junction. It is I is equal to I1 plus I2 plus I3. And for Kirchhoff's second law, it is the conservation of energy. That is, the sum of the EMF is equal to the sum of the potential difference across a closed loop. So around a closed loop, the sum of the EMF is equal to the sum of the potential difference. EMF is equal to the sum of the potential difference. This is for the second law. And what is the conservation for the second law? This is the conservation of energy. A circuit contains a cell of internal resistance R and two resistors R1 and R2 as shown in figure 5.1. So internal resistance R and R1 and R2, the potential difference across two resistors is V. So the potential difference across the two resistors R1 and R2 is V. The current in the cell is I. So the current entering the junction is I. Use Kirchhoff's law to show the total resistance of the external circuit is given by this formula. So here we can say that 1 by RT is equal to 1 by R1 plus 1 by R2. So we need to show this equation. So we know that the current entering a junction is equal to the sum of the current leaving a junction. That is, I is equal to I1 plus I2. I1 plus I2. I is equal to I1 plus I2. So the current I is equal to I1 plus I2. That is, V by R. Current is equal to resistance is equal to voltage by current. So current is equal to voltage by resistance, and V by R total is equal to V by R1 plus V by R2. And since the voltage is same, since the two resistors are arranged in parallel, so as we can see that the two resistors are arranged in parallel, so the voltage is same as V. That is V, and so the initial voltage that is coming is also V. So as they are arranged in parallel, so the voltage is same, that is V. So, and if both the voltages are combined, that is, the combined voltage is also V. That is, if they are joined, then it is V, and this is also V. So V by R total is equal to V by R1 plus V by R2. So if we cancel the V, then 1 by R total is equal to 1 by R1 plus 1 by R2 as shown. In part 2, the electromotive force EMF of the cell is given. So the EMF of the cell is given, that is 1.5. So the EMF of the cell is 1.5 volt. So the EMF is 1.5 volt. When the values of R1 and R2 are 10 ohm and 15 ohm. So when R1 and R2 are 10 ohm and 15 ohm, that is R1 is 10 ohm and R2 is 15 ohm respectively, the potential difference measured by the voltmeter is given, that is 1.38. So potential difference across R1 and R2 is 1.38. That is, the voltmeter is connected across R1 and R2. So the potential difference in the voltmeter is 1.38 volt. So calculate the internal resistance of the cell. So to calculate the value of internal resistance, we know that resistance is equal to voltage by current. So to find the value of internal resistance, first of all we need to find the value of voltage and the value of current. So what is the voltage across the internal resistance? So we know that EMF is equal to potential difference across the internal resistance and the plus terminal potential difference. So EMF is equal to potential difference across the internal resistance plus terminal potential difference. That is, here we can see that the total EMF is equal to the potential difference across the internal resistance plus the terminal potential difference, that is across the terminals of the cell. So the total EMF is equal to the potential difference across the internal resistance plus the terminal potential difference, that means across the terminals of the cell. So we know the value of EMF, that is the total EMF, and the terminal potential difference is 1.38. That is the total terminal potential difference is 1.38, and there is no other resistor, so it is 1.38 volt. So the EMF is 1.5 volt. EMF is 1.5 volt, that is 1.5 is equal to potential difference plus potential difference across the internal resistance plus terminal potential difference, that is 1.38 and 1.5. So potential difference across the internal resistance is equal to EMF minus terminal potential difference. So we get the potential difference across the internal resistance. Now we need to find the current across the internal resistance. So what is the value of current across this internal resistance? So first of all, since we have given the value of two resistance, we can calculate the combined resistance. Now after calculating the combined resistance, since we know the value of voltage, so we can easily calculate the value of current. So first of all, 1 by R total is equal to 1 by R1 plus 1 by R2 for parallel combination of R1 and R2. So we calculate the combined resistance, and for this combined resistance, we need to find the value of current. This current is equal to voltage by resistance, and the combined voltage for this combination is 1.38 and the combined resistance is 6 ohm. That means the combined voltage is 1.38 and the combined resistance is 6 ohm. So what is the value of the current? That is I. I is equal to voltage by current. Current is equal to voltage by resistance. So voltage, that is 1.38 by the resistance, we get the value of current. Now we have to find the value of current. Now that is the value of I. Now since for this combination we can see that the total combination is a series combination, that is this total combination is a series. So after calculating this value, now the total combination that remains is the series combination. So for the series combination, so for this series, since the current is same in series circuit, so the current is same in the series circuit, there is the current in this place is also the current is in this place. There is the current across the internal resistance. So the current is same as I, and what is the value of current? Current that we get is 0.23. So we have find the value of current and we have found the voltage. Now by using the formula resistance is equal to voltage by current, there is a voltage across the internal resistance by the total current. There is in series, the current remains the same. So the current is same. So the resistance that we get is 0.5217, that is approximately 0.52 ohm. So the internal resistance is 0.52 ohm. A third resistor is added in parallel with R1 and R2. In the circuit shown in figure 5.1, Sten explained the effect, if any, of this change on the current in the cell. So a third resistor is arranged in parallel with R1 and R2. So a third resistor is arranged in parallel with R1 and R2. Suppose this is R1, this is R2, and now we have added an additional resistor, that is another resistance R1, R2, and an unknown resistor. So what happens to the current of the cell? There is the current I. So what happens to the current I? Now to find the value of current, first of all, let's consider the two situations that if we consider the both the resistance as 2 ohm, so if the both the resistance are 2 ohm, there is 2 ohm, so this would also be 2 ohm, there is 2 ohm, 2 ohm and 2 ohm. So for parallel combination we know that 1 by R total is equal to 1 by R1 plus 1 by R2. So R is equal to, R total is equal to 1 by R1 plus 1 by R2 inverse. So for this situation, we need to find the combined resistance, that is the combined resistance that is 1 by 2 ohm plus 1 by 2 ohm inverse. So the combined resistance is 1 ohm for these two resistors. Now for the three resistors that is in parallel, so R total is equal to 1 by 2 ohm plus 1 by 2 ohm plus 1 by 2 ohm inverse. So what is the combined resistance that we get? So the combined resistance that we get is 0.666. So we can see clearly that for 2 resistor the resistance is more, but for 3 resistor the resistance is less. That means in parallel combination, if we add more resistors, then the resistance value decreases. So the total resistance value decreases. That is, for parallel combination, if we add some additional resistor, the resistance decreases. So that means the combined resistance decreases if we add additional resistor in parallel combination. So you have to remember that this is important, that if we add some additional resistor in parallel, for parallel, if we add some additional resistor, then the total resistance, that is R total, decreases. So since we have added a third resistor, so the total resistance decreases, and since the total resistance decreases, so we know that resistance is equal to voltage by current. As the total resistance decreases, so the total current must increase, since resistance is inversely proportional to current. So as the total resistance has decreased due to additional resistor in parallel and the EMF is unchanged, so the EMF is same because the EMF is provided by the battery, and since the battery is same, that is the battery is same, so the EMF would also be the same. So the EMF is same, so the current in the cell will increase. As the resistance decreases, the current increases. The potential difference measured by the voltmeter. Initially we have found that as the total resistance has decreased, so the current increases. As the current increases, now what happens to the potential difference measured by the voltmeter? So potential difference measured by the voltmeter, that is this potential difference measured by the voltmeter. So we have found that the current increases. As the resistance decreases, total resistance decreases, so the current increases. And as current increases, you have to remember that as the current increases, the lost volt increases. As current increases, so the lost volt increases. And we know that EMF is equal to potential difference across the internal resistance. That means the lost volt plus the potential difference across the terminal potential difference. That is the potential difference or the terminal potential difference. So EMF is equal to potential difference across the internal resistance or lost volt plus terminal potential difference. And here we can see that as the current increases, so V is equal to IR. So since current increases, so the potential difference across the internal resistance increases. As current increases, so potential difference across the internal resistance increases, that is this internal resistance increases. And since the potential difference across the internal resistance increases, so the EMF is constant, and potential difference across the internal resistance increases, EMF is constant. That means the potential difference across the terminal potential difference decreases, or the potential difference measured by the voltmeter decreases. So here we can see that the current increases, and as we have added an additional resistor in parallel, so the total resistance decreases. As the resistance decreases, current increases, and as current increases, lost volt, that is V is equal to IR, increases. Since current increases, so lost volt increases, or the potential difference across the internal resistance increases. And since the potential difference across the internal resistance increases, so internal resistance increases, EMF is constant, so the potential difference across the external resistance or the terminal potential difference must decrease in order to reduce this increase. So the potential difference measured by the voltmeter decreases. So the potential difference measured by the voltmeter decreases. You also have to remember the steps of this question because this is an important question and you have to remember the steps. That is, if the current increases, then the lost volt increases, and as lost volt increases, so the potential difference across the external resistors decreases. For question 6, nuclei of an isotope of Sm each contain 62 protons and 85 neutrons. State the nuclear notation in the form of AXZ for this isotope of Sm. So you have to remember that A is the nuclear number or the mass number. So nuclear number or the mass number, that is the number of protons plus the number of neutrons. Proton plus neutron is the nuclear number or mass number, and Z represents the proton number or atomic number. So Z represents the proton number or atomic number, that is proton, and nuclear number or mass number is A, that is the number of neutrons plus number of protons. So Sm is our symbol for the element, and Z A is a proton plus neutron. So proton plus neutron is 147. That is, if we add this value, we get a value of 147. And what is the proton number Z? Proton number is 62. So this is the nuclear notation for this element. Now, this isotope of Sm is radioactive and decays by emitting particles. Gamma radiation is not emitted. So gamma radiation is not emitted. The energy spectrum of the emitted particle is shown in figure 6.1. So this is shown. Explain how figure 6.1 shows that this isotope of Sm emits alpha particle and does not emit beta particle. So why we can say that this emission is the alpha particle? So alpha emission, because here we can say that the kinetic energy of the particle is same. So the kinetic energy value is the same. So since alpha particles have discrete amount of energy, or alpha particle have discrete amount of energy or the same amount of energy, but for beta particle, you have to remember that beta particles have a continuous range of energy. So alpha particles have discrete amount of energy, and for beta particle, they have continuous range of energy. So the energy for beta particle have a continuous range. So for the energy for beta particle, they have a continuous range. Since they have a continuous range, but for here we can see that the energy is same or discrete. Since the energy is same or discrete, so this is obviously an alpha emission and not an beta emission. And for beta emission, the particles have continuous range of energy. Suppose like this, they have a continuous range. That is, some particles may have a big energy, then small, then big, small, then like this. But for alpha particle, they have a discrete amount of energy or the same amount of energy. So the kinetic energy of the particle is discrete or has only one value. So has only one value or discrete. Therefore, we can say that the emission is alpha particle. But for beta particle, they have continuous range of energy. So beta particle have continuous range of energy, but for alpha particle, they have discrete amount of energy. This isotope of Sm decays to an isotope of Nd. So Sm decays to form Nd. Give the radioactive decay for equation for this decay. Include the nucleon and proton number of all the particles involved. So here we can say that the emission is alpha emission. So the emission is alpha emission, that means alpha particles are emitted, and we know that alpha particles have a proton number of 2 and a nuclear number of 4, that is proton plus neutron, and Sm is 147 and 62. So 147 and 62 decays to form 4 and 2. So 147 minus 4, so 147 minus 4, that is 143, and 62 minus 2, that is 60. So this is the overall decay equation. For part C, a baryon is composed of 3 quarks which all have different flavors. So different flavors means that one is up, top, charm, down, strange, bottom. That means since the flavor is different, so up is one flavor, top is another flavor, charm is another flavor, down is another flavor, strange is another, and bottom is another. They all are different flavors. The baryon has a charge of 0, that means the overall charge is 0. 2 of the quarks in the baryon are an up quark and a bottom quark. So one flavor is up quark and the other flavor is bottom quark. There is one is up and another is bottom. Determine in terms of elementary charge E the charge of the third quark of the baryon. So we need to find the charge of the third quark. So you have to remember that for up, top and charm, the charge is plus 2 by 3e. For up, top and charm, up, top, charm, the charge is plus 2 by 3, and for down strange bottom, the charge is negative 1 by 3. So for up, top, and chirp, the charge is plus 2 by 3, and for down strange and bottom, the charge is negative 1 by 3. So initially we get an up quark that is plus 2 by 3 and a bottom quark that is negative 1 by 3, and we refer the third quark as Q, or we represent this as Q. Now what is the value of the third quark? Now you have to remember that the overall charge is 0, so we equate this to 0. There is the overall charge is 0. So after calculating, we get a value of Q that is negative 1 by 3. So it is negative 1 by 3 E. State a flavor for the third quark of the baryon. So what is the flavor of the third quark? Now you have to remember that initially it is mentioned that all have different flavors. Since all have different flavor, it is already mentioned, that means the flavor must be different. So since it is negative 1 by 3, so it can be any of the three, but since the flavor is different and we have already used bottom, so we have already used bottom, now the remaining two flavor is down or strange. So you can write any of this value, but you cannot write bottom because they have different flavors. So you cannot write bottom, but you can write down or strange any of these values or any of the quark.